Hello everyone and good evening. Welcome to the OneClass channel. My name is Fejiro and I'm an Honors Bachelor of Science graduate currently working towards medical school. Today I'll be doing my best to go over some commonly asked chemistry questions at both the high school and college levels. If you need some homework help or tutoring or just some further clarifications on the topics we cover today, please check out the links in the description below, okay? And with that being said, let's kick it off for this session with our first question of the evening. Hopefully the camera actually did change. All right, so we have, what are the diatomic elements and what does it mean to be diatomic? Diatomic elements. What does it mean? So with this, I'm sure you can see in the screen as well based on what my colleagues said in terms of identifying the diatomic elements, but we'll actually use this to help with the explanation, okay? What do you notice? We have H2, N2, O2, F2, Cl2, Br2, and I2, okay? So now, with that being said, if I wrote something like this, 2O, would this be a diatomic element? In my opinion, no. The reason being is because this represents something else. This is saying, rather than having oxygen bonded, like an oxygen molecule, this is saying we have two oxygens. Something like this is probably what you would see when you're writing like your equations and such. Like for example, if I said CH4 plus O2 turns into CO2 plus H2O, we'd have some things in front of it. So right here, this oxygen is indeed a diatomic element, but putting a number in front of it like this is not going to make a diatomic element, okay? This just means there's two oxygen molecules. The reason why I'm bringing this up is because the coefficient, okay, the number in front is not what makes a diatomic element. If you look closely, it's actually the subscript after the number, which identifies it as a diatomic element. And now, this is where we focus on the part that says di. Di, not D-I-E. So with that being said, di, in terms of the, I believe it's Latin or Greek, but for the prefix, it typically means two, okay? So that's what they have all in common. These diatomic elements all have that subscript of 2 after each one, okay? That is what makes these diatomic elements. The reason why these ones were picked is not random. These are what occur in nature, okay? So I know that was just a lot of information, so let's just quickly go over it, okay? So diatomic elements, to my best capability of writing this out, are elements that occur in nature in pairs. Okay? What do I mean by that? I mean that if I said I had an oxygen molecule, I would not be talking about this. I wouldn't be talking about this. This is like ozone. I'd be talking about the diatomic element O2. Okay? This right here is what we refer to as an oxygen molecule, because this is something that occurs naturally and it comes in pairs. Same thing with the fluorine gas, for example, F2. If I said we have fluorine gas molecules, that will be F2. This is a diatomic element. The same thing applies to all of these, and it does touch base on what it means to be diatomic. As my colleague said, it means that the molecule is composed of two of the same elements bonded together. That part is very key. They have to be the same element. If I put, trying to think of two molecules that can be together, HF, okay? This is not a diatomic element. This is known as, if I remember correctly, hydrofluoric acid, okay? And this is not a diatomic element because the hydrogen and the fluorine are different. This is not what we count. They have to be the same thing. So pretty much try your best to think of it enter it this way. If I wrote Br, I would not put 2Br, okay? If they were bonded and everything, this is what we had. It would actually be Br2. This is a proper representation of a diatomic element. It's not the same thing as if I was doing like HBr plus H2O, because it dissociates and we have H3O plus Br minus, something like that. Okay, if I doubled everything, this is when you may see like things like 2Br minus, but these are ions. In fact, this is still not considered diatomic elements. The key thing I'm trying to stress here is that you want to be able to see this subscript. Whoops, sorry, not for this one, that's ozone. Technically, I believe it might even be called a triatomic element, but that's not the question it's asking here, and I may be wrong. Let's just focus on the diatomic ones, which I am confident with, is that we have the 2 as the subscript, okay? And now let's go to the periodic table so we can actually identify them. These are the ones that we know occur typically in nature. So you have hydrogen right here, okay? The hydrogen gas right up top. Then we have kind of like this upside down L, or if anything, it'll be like an arrow. The NOF, Cl, Br, and then I actually. So it would actually be best to say it's upside down L. So if I were to, I guess, map out the diatomic elements on the periodic table, it'd be the hydrogen on one end, and then we have 7 more. 3, 4, 5. Oh, maybe it's actually 6. 1, 2, 3. Oh, it is 6. So like this, okay? Upside down L. This should correspond with the elements on the periodic table. I would get as familiar as you can with these as possible. Possibly just even straight up memorize, because these are referred to frequently, especially things like when they mention oxygen gas or even nitrogen gas. Typically you want to remember that you're working with O2, because this is how you would also calculate the molar mass of it. You don't want to go to a question where it says I have a certain amount of oxygen gas and you say, oh, that means it's 16 grams per mole. You'd have to double it because it's diatomic elements. An oxygen molecule actually has 32 grams per mole because it's a diatomic element. So that is quite a bit of information to process, so I'll just stress this part. Elements that occur in nature in pairs. These are diatomic elements, and you are looking for the subscript right here. Okay? With that being said, this is correct. Let's move on to the next question. So question number 2. We have a temperature of 25 degrees Celsius is equivalent to 75 degrees Fahrenheit. So 25 degrees C is equal to 77 degrees F. And 40 degrees Celsius is equal to 104 degrees Fahrenheit. Assuming that it's a linear relationship, we want to find an equation that relates the degrees of Fahrenheit to degrees of Celsius. So for this, I'm just going to actually, it doesn't really say, but I'm going to use Fahrenheit as my rise and Celsius as my run. What do I mean? I'm going to assign these as my y and these as my x. So in order to find the slope, what I have to do is the rise over run. So it's going to be 104 minus 77 divided by 40 minus 25. And this is all to find the slope of this relationship between Fahrenheit and Celsius. So 104 minus 77, we have 27. And 40 minus 25 is 15. So for every 15x difference, there is a 27 y difference. And if we simplify this, I do believe we get 9 over 5. Yes, we do. 9 over 5. Okay, that is the most simplified form. And this would be the m, the slope. So exactly, whenever x increases about 5 degrees Celsius, there's a 9 degree change in Fahrenheit. Now, as we know, our slope intercept formula is y is equal to mx plus b. So see, we're getting a little bit into the math realm here, but these are some of the examples you have to use in terms of working with temperatures, because let's say for some reason you're trying to find pressures difference, but they gave you Fahrenheit. You'd have to convert the Fahrenheit into Celsius and the Celsius into Kelvin in order for you to use your PV equals nRT. So there is always going to be a level of math involved in chemistry. That's just how it works. Whether that's fortunate or unfortunate for you depends on how proficient you are in math. So with that being said, y equals mx plus b. I'm going to go ahead and plug in the two numbers here, the 25 and the 77, to be able to find out the proper b, in a sense, our intercept, our y-intercept. So we have 77 is equal to 9 over 5 25 plus b. So 25 times 9 over 5 is just 5 times 9. And we do get 45. So 77 is equal to 45 plus b. So that'll be minus 45 on both sides. Okay, and then we get 32. B is conveniently 32. And for those that actually do know the conversion between Celsius and Fahrenheit, this is actually almost word by word the conversion. It's y is equal to 9 over 5x plus 32. This is how you would convert Celsius to Fahrenheit. Now, that is the equation we're to find. So we've solved the first part of the question, okay? So now they want us to also find the temperature in which both measurements are the same. So what they're saying here is that the Celsius equals a Fahrenheit, aka y is also equal to x. So that logic applies. There you can pretty much replace these with any of them and just say x is equal to 9x over 5 plus 32. So we subtract, actually, just to make it easier on us, 9x over 5 from both sides. So what we're left with is negative 4x over 5 is equal to 32. So then we have to multiply by 5 divided by 4. Okay? And we get, and make sure it's negative actually, almost forgot that, because we're going to cancel the negatives. So these are now canceled. And what we get here though is that x is equal to negative 40. It could be Celsius or Fahrenheit. Because we decided that x is our Celsius, we say x is negative 40 degrees Celsius. And you would see actually that based on this equation, that when x is negative 40 degrees, y should also be the same thing. Because if we plugged it into this equation, we have 9 times negative 40 divided by 5. Just to make sure, yep, divided by 5. I feel like I did something wrong. Negative 40. Oh, I know I said 2 over there, that's why. So 9 times negative 40 divided by 5, there we go, plus 32. And we get negative 40 as well. So when x is negative 40 degrees Celsius, y is actually also negative 40 degrees Fahrenheit. So just like that, we were able to solve this question. Not only do we get the linear relationship, we also find the degrees where they would both equal each other. So just like how our colleague did, we found the slope based on the rise over run, and it was 9 over 5. And then we plugged in some of the numbers to find that b, okay, which was ended up being 32. And then they made the Fahrenheit equal Celsius, so they were to replace it, and with that they got that when both measurements are negative 40, that's when they equal each other. So with that being said, this is also correct. And now let's move on to question number 3. So for question 3, we have calculate the molar mass of potassium hydroxide. So molar mass of KOH. Luckily, they were nice enough to actually give us the name of potassium hydroxide. which makes it a lot easier. I mean the molecular formula. But in case they didn't, if they really just said potassium hydroxide, this is one of the things that you do have to memorize. Not the potassium, because that's relatively straightforward, but hydroxide specifically is an ion. It's a polyatomic ion, which is OH, because there's two atoms in it, oxygen and hydrogen. And the reason why it's an ion, because this has a negative charge, which is -1. This right here is a hydroxide. And if we know that potassium is just K, and it prefers to just give away one electron, to balance these two out, you do just get KOH. Now with that being said, this question is asking for the molar mass. So here is where we have to list out our constituents so that we can actually add them up together to get the molar mass. So we have 1 potassium, 1 oxygen, and 1 hydrogen. So for this one, it's relatively straightforward because there's only one of each. But you have to make sure you add everything correctly. So that's 39.098. Oxygen was 15.999. Hydrogen is 1.008. And right now we're just doing the multiplication stage before we add anything, because in the off chance these were different numbers, you want to make sure you're always multiplying first before you just start adding things. Okay, so 39.098, 15.999, 1.008. So that's KOH. So let's use a calculator now. We have 39.098 plus 15.999 plus 1.008, and we get a lovely number of 56.105. Now here's the most important part actually, well at least the second most important. Other than actually adding things together, you cannot forget your units. And here it's always grams per mole. Because what you've said is that for every mole of potassium hydroxide, we have this amount of grams based on how many grams per mole of each of its parts. Okay, let's see how we did now. So with that being said, thankfully we got the exact same answer as our colleague because they just added the constituents. And this would be how you find the molar mass of potassium hydroxide. So now for question number 4, we have, what is the molar mass of calcium hydroxide? Now, with this, as discussed in the previous question, I'm going to go ahead and restate it. If we were not given the molecular formula of calcium hydroxide, the way we have to find this is by understanding what hydroxide is, which comes from practice and memorization, because hydroxide is a polyatomic ion, just OH, and it has a charge of just a -1. Okay? But as you know, calcium is on the second column. So because of that, calcium, alright, has 2+, because it has to get rid of 2 electrons. So in order for these cations and anions to actually balance, as the thing says, we need 2 hydroxides, which is how we get CaOH2. So now the same thing is going to apply here to where we add up the constituents, okay? So we have 1 calcium, but here you have to be careful. The 2 actually multiplies into both. So you have 2 oxygen and 2 hydrogen. So let's go back to the periodic table. Calcium is at 40.078. Oxygen is at 15.999 and 1.008 for hydrogen. So now we have to make sure we do the multiplication step first. Since calcium was 1, we have the same thing. Oxygen is now 2 times that, so that would be 31.998. And this is also 2.016. Now we can safely add, okay? And we get 40.078 plus 31.998 plus 2.016, 74.092, and still very important, do not forget your units of grams per mole. Okay, because it's pretty much saying that for every mole of calcium hydroxide, we have the grams for each of its constituents, the calcium, the oxygens, and the hydrogens. Okay, so let's see here. Based on this, which is the best choice? I would say our answer is C, because that's the closest thing to 74. So see how we did. Yep, 40.078, 15.999, 1.078, and then they just added together. They make sure that they divided the they multiplied the oxygen and the hydrogen by 2, and that is how they got specifically this answer here. Now, with that being said, that is correct, and we do indeed end up with C. It's time for question number 5. For this question, we have BeCl2, so that's beryllium chloride, has an incomplete octet around beryllium. And now they're asking us to draw the Lewis structure. So Lewis for BeCl2. So they did give us quite a big hint here. Be, beryllium, is an incomplete octet. What does that mean? It means that it's not going to follow the octet rule to where it has 8 electrons surrounding it. Okay, it's going to be less than that, because that's what incomplete means. So let's go ahead and see how many valence electrons each molecule contributes, so that we can get an idea of how many valence electrons we're working with total. So we have beryllium conveniently on the second column. So that'll be 2 electrons. Chlorine, on the other hand, is all the way in the 17th column. So we have 7 electrons times 2. So that'll be 14. Might need some water. Together we have 16 electrons to work with. Now, beryllium, I'm going to go ahead and put in the middle, because not only is it the unique one, but you will see based on its orientation that it has the, I guess, the most bonding chances, having quote-unquote 2 unpaired electrons. Technically speaking, we can use beryllium in the middle. So we have Cl, Be, Cl. Now, let's go ahead and fill in the rest of the outer electrons here. So for the chlorine, right now in that single bond is sharing one of its 7. So it'll be 2, 3, 4, 5, 6, 7. Same over here, 2, 3, 4, 5, 6, 7. And now the beryllium, okay, this one, as we said, only has 2 valence electrons, and funny enough, it's already sharing 2 of its 2 electrons. So it's actually done right there. So now let's go over to make sure we actually have the right, information. Do we have 16 electrons? Well, considering we have 2 bonds and 6 lone pairs, together I do believe we have 16 electrons, so that's good. Does everything else other than beryllium follow the octet rule? According to chlorines, they also do. Are the formal charges as close or just 0 for each molecule? For each atom. Well, let's see. So beryllium, in its natural state, where it has a formal charge of 0, just has 2 single bonds, or at least just 2 bonds in total. Okay. Chlorine, on the other hand, would like to have 3 lone pairs and 1 bond. Based on this, and based on the pictures I've drawn, everything here is actually going to be in its formal charge of 0. So with all that being said, this is the most stable Lewis structure I can think of for beryllium chloride. Okay, and let's see how our colleague did in regards to this question. They drew the skeletal structure, then they had 1 bond in between them, and then they filled in the rest of the octet. So this is indeed perfect. So that being said, this is correct. And now we're done with question number 5 and are good to move on to question 6. But quickly, let me just see how the stream is doing. Okay, we are doing good so far. Hopefully it's clear quality on your end. Let's see, let's continue. We have this interesting conceptual question here for 6. Write the name for iron sulfide. Well, almost gave the answer away there. So write name for FeS. So for this, we have to understand what the iron and the sulfur are, okay? Sulfur is relatively straightforward, okay? We want a sulfur ion, but if you remember your naming rules, these things cannot just end with sulfur. All of these are typically replaced right here with an IDE. So that would be sulfide. It's something sulfide. Let's look at what we have so far. It can't be A or B. That's it. It cannot be A or B because those ones do not end in sulfide. So we're able to narrow this a little bit more down. Now, A, B, or D. There we go. Cannot be A, cannot be B, cannot be D. Why? Because those ones say sulfate. So we need iron 2 sulfide, iron sulfide, or iron 1 sulfide. Now you're probably wondering what these, I guess, Greek numbers, Greek letters, what do those mean? Okay, so sulfide, okay, the sulfur ion, all right, if you look at the periodic table, it's on the 16th column, okay? That means it has 6 valence electrons. For it to fill a complete octet, it just needs 2 more. So we would typically see S2-, okay? Now, if you want the total charge to have a net of 0, what does the iron have to be? Iron literally has to be Fe2+. Now, with that being said though, there are the different names we saw, but why does this charge matter? Well, let's look at where iron is on the periodic table. And as I suspected, it's a transition metal. What does it mean to be transition metal? It means that you have multiple choices of electrons you can typically give away. Okay? So with that being said, the iron in this case is choosing to give away 2 rather than like maybe 3 or 4 or whatever occurs in nature. It's choosing to give 2. Now, with transition metals, they have a specific naming structure to indicate how many they are given. And you probably guessed it, it's based on those Greek numbers or / letters, not really sure. So with that being said, we're right here looking for iron 2. Why 2? Because it's a 2+. So the total name we have for this really is iron 2 sulfide. That would be the correct name for this. So which one would that be? We're looking through. It cannot be A, B, or D. So C, E, or F. E doesn't even include the 2. F is the wrong number. So E, just as a clarification, may have worked if iron was not a transition metal. Let's say it was like calcium or something. So CaS. You are free to just call it calcium sulfide. You do not need to indicate. But with transition metals that have multiple forms of cations or even anions, you need to indicate which one you're working with in order for the question to be fully understood. So with that being said, that's how the only answer you can use here is C, which is iron 2 sulfide, okay? And the last thing I would say in regards to this before we look at what our colleague did is the reason why I didn't pick sulfate or anything like that is not just because a sulfide ends with an IDE, but sulfates, which are also real things, those are different. That is a sulfur bonded with a certain amount of oxygens. In that case, sulfate will be 4. It will be SO4. Okay? So, with that being said, though, the answer is C. Let's see how our colleague did. Yep, they just said the correct answer is iron 2 sulfide or ferrous sulfide. And the correct answer is indeed C. Alright, so this is correct. Let me just take a quick water break here. And now we have question number 7. Okay, this one's kind of a bit of a doozy here because multiple steps. But we have given the molar mass, so molar mass of H3PO4 is 97.994 grams per mole. Cannot forget the per mole part. Don't do that. Determine the number of grams of H3PO4 needed to prepare 1.5 liters of a 0.25 molarity H3PO4 solution. And they want us to show our work as well. And then they want to know what volume in liters of that solution can be prepared by diluting now the 1.75 molarity H3PO4 solution. And once again, we show our work. So we're going to solve A and B accordingly, okay? So although they give us the molar mass as a first part of the question, we're actually going to say that to the last part of at least question A. We want to find out how many moles we actually have. And they're actually really kind to us because they gave us a molarity and a volume amount, in this case liters, okay? And if we remember, okay, molarity, the big M, is equal to N over L, moles per liter. So if you want to find the moles, it'd be moles is equal to molarity times liters, okay? So with that being said, in this case, let's write it out fully. We have 0.25, I guess, moles per liter. We're actually going to start with the liters first, actually. I think that would be easier. So we have 1.50 liters times, okay, the molarity, which is 0.25. Let me see here. Moles per liter. Alright? And then they want us to actually find the number of grams in total. So I'll actually add an extra step. I'd be going from moles to grams. So that would be using the molar mass. Because for 1 mole of H3PO4, we have 97.994 grams. Okay? And now, as you can see, theoretically, the liters cancel out, the moles cancel out. All we're left with is the grams. Now we have to see if we actually did it correctly. So 1.50 times 0.25 times 97.994. We have the total grams, okay, is 36.75. Okay. And now the question is asking the volume in liters for 1 molarity solution to be prepared by diluting 50 mils of another molarity solution. Okay. Now they're asking us to show our work. So with this one, actually, we'd actually want to use this formula here. C1V1 is equal to C2V2. So with that being said, we're going to actually use, I guess, the 1 as the 50 mils and the 1.75 molarity. So that'd be 50, or at least 50 mils. If we converted that into liters, it'd be, maybe just be 1, 2, 3. Yep, that's correct. it'd be 0.050 liters times, and the V1, whoops, that is the V1. The C1 will be 1.75 molarity of H3PO4. And that has to equal C2 V2. And because we already know the concentration, which is 0.025, we just divide both sides by C2, the concentration, to see what we get. And we get, if this is 0.25, we have 0.050 divided by 0.25 times 1.75. We have 0.35. So volume 2 is equal to 0.35 liters though, okay? So that means we actually have quite a bit. It would actually be, in this case, 350 milliliters. And we'll see what we can do with that. Let's compare with our colleague here. We have, 97.994. And then they're able to do that in order to get the 36.75 grams. So that is perfect. That's what we're looking for. Now for the next part, 50 mils, 1.75, 0.25, and it was indeed C1V1 is equal to C2V2, and you can see that is 0.35 liters, which is also known as 350 milliliters, okay? So with that being said, this is also correct. This is correct. So now we move on to question number 8. We have calculate the molar mass. So molar mass of methanol. Okay. So with this, actually is a little bit tricky. I do want to say memorize it, but this is definitely more like the organic chemistry side to identify what methanol is. Nonetheless, we're still going to try to see if we can spread some further understanding of it. So with that being said, okay, we have the molecule methane, CH4. Okay, what does this look like? It's just this, okay, with 4 hydrogens on each corner. Now, what happens with methanol instead of methane is that now we replaced one of the hydrogens with a hydroxide group, which is the OH minus. So instead of it being like this, where it's just an H on each side, we have now an OH, okay? And that is actually how you get the formula for CH3OH, because literally speaking, there is carbon and then 3 hydrogens and then OH right there. Now, let's go ahead and find out what the molar mass is based on its constituents. I'm sure you can see the answer there. I just wanted to go over with how you'd even identify what methanol would be. With that being said, though, we have 1 carbon, 3 hydrogen, 1 oxygen, and I guess instead of saying 3 hydrogen, we can just erase that and put 4 hydrogen, okay? So, let's see. We have times 12.011 times 1.008 times 15.999, okay? And because most of these are 1s, the other 2 will remain relatively, if not exactly the same. But the hydrogen, there's 4 of them, so to multiply by 4. So it'll be 12.011, 15.999, and now, let me just check, it'll be 4.032, okay? So, let's go ahead and add these all up and see what we get. We have 12.011 plus 4.032 plus 15.999. Okay? I feel like we're missing something here. Because CH3OH. 4.032. That's why. I thought I put a 4, but my calculator said 1. There we go. And we get 32.042. And you cannot forget your units, grams per mole. That is always very crucial. And now, that will be our molar mass of methanol. Let's see how our colleague did here. So, according to our colleague, yep, they did exactly the same way. They made sure to multiply the hydrogen by that 4, since there was 4 of them. And then everything else was 1. And they got around the same answer as me, with only a slight variation, most likely due to the periodic table they're using. Okay? I don't believe any one periodic table is like the exact, correct Bible, like that's what you refer to. But at the same time, I do stress the importance of staying consistent. So whichever periodic table you use in the beginning of the question, or like even the beginning of your term, I would try my best to stick with that periodic table, so that way your numbers are as relationship-wise close to each other as, well, I guess close to, your numbers relate to each other as much as possible, okay? Because I don't want to get like a carbon from one periodic table and then pull out an oxygen from a different one, okay? You want to keep it all localized in the same periodic table. So with that being said though, this is correct. Let's move on to question number 9, okay? We have, what is a Lewis structure of BeH2, okay? So for this one, if for those that were able to see it, this is very similar to how we did the BeCl2, okay? But let's go ahead and draw this out. So BeH2 Lewis. Okay, so let's first find out how many electrons does each contribute. Beryllium being on the second column would only be 2, and hydrogen being on the first column would only be 1, but because there's 2 of them, that would be now 2. So that's 2 plus 2, and that's how we have 4 for this question right here. Now, with that being said though, how do we then go on to find the total molar mass? That one would be, sorry, not molar mass. How do we go about finding in terms of the total electrons? That would be 4 electrons. And then we just put beryllium in the middle. Why beryllium? Because beryllium is the only unique one in this case. So we would have H, Be, H. Now the next part is fill in the octets, okay? So with that being said, hydrogen is literally already sharing one of its 1 electron it wants to share. Both hydrogens are doing that. And the beryllium is actually already sharing 2 of its 2 electrons they want to share. So for this, you could actually argue that this is pretty much it, all we need for the beryllium hydride. But, okay, this is a but now, is that we have to make sure that this formal charges are also good to go, okay? So what does that mean? It means that what I'm going to do here is compare these with like a natural, I guess, 0 formal charge version of them. So hydrogen at 0 formal charge has 1 bond. So that's good, that's what hydrogen is doing. Beryllium, on the other hand, because it had 2 lone pairs, this would be its most, well, its time where it would only have 2 bonds. That would be when the what's it called? When the net sorry, just using the word actually. When the net formal charge is 0, okay? That is when you know that you made the right choice, okay? And that's what we have here. Both net formal charges are 0, so this would be the beryllium hydride Lewis structure, okay? So now with that being said, let's see how our colleague did. We have, there we go, the HBeH as the Lewis structure, okay? Let's see what else was said. All right, 2 electrons, total 4 electrons, and then they went on to solve the actual geometry. Okay, good. So this is correct. Let's go on to question number 10. We have another Lewis structure question, a little bit more complicated this time. What is the Lewis structure of xenon tetroxide, or xenon tetroxide? There we go. And we want to know the Lewis structure. So let's write it out. Lewis of xenon tetroxide. Okay, so for this one, we first have to know how many of the constituents we're working with. So xenon, okay, actually start with oxygen first. Oxygen has 6 valence electrons, meaning in this case it will be contributing 24. Okay, now with the xenon, the one thing is that actually it has already a valence electrons of 8, meaning that it's completely filled. But here's the part that's tricky about it, is that this time when it does form bonds, as it's doing here, it kind of throws away the octet book out the door, and you kind of just solve it by hand. So with that being said, we cannot follow an octet rule here. So let's go ahead and try to label things out as much as possible. We have 8, so in total we're looking for 32 electrons. Okay, so with that being said, xenon's in the middle. Okay, we have 4 oxygens. 1, 2, 3, 4. Okay, and now we want to add the oxygens, and then we wanted to go ahead and count out the number of lone pairs. I mean, not lone pairs, the number of valence electrons that it had, and how much is sharing and how much is still needed. So for this, the oxygen, it has, trying to figure out what the color coordination would be, but let's just go ahead. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. Okay, so we have a lot of unpaired electrons here. Now with xenon, it's right now sharing of its 4 of its 4. So I could theoretically just do this: 1, 2, 3, 4, and each, to be able to resolve that single bond, turn each to a double bond. Okay, so that'll be this. Okay, and then we have this double bond as well, and this last double bond we have. Oops, I got a little greedy here. That's what happened. So with this double bond here up the top, we have these two, and then the from the sides we have these. Nope, wrong one again. These two, because we want to know from down we have these two. Okay, so this is a quick summary. We got rid of the unpaired electrons, and they're all just going to form a double bond with the xenon in the middle. Okay, so that being said, we have xenon in the middle. Okay, let's put it a little bit lower because we need that extra space. And now we're going to have the double bonds on each oxygen. Okay, and you can't forget your lone pairs. And now we'll see if we can actually have, well, not we can, if we actually have the right amount of electrons. So let's see. We want 32 electrons. We have in total 8 bonds, because that's 4 double bonds, and 2, 4, 6, 8. 8 bonds and 8 lone pairs. Okay, double everything, you end up indeed with 32. Okay, so that is correct. Now let's see if we actually were able to keep the formal charges at 0. Okay, let's see here for this little structure. Oxygen likes to have like that. That would be a normal charge of 0 for oxygen, okay? And we want our best to keep it that way as long as possible. Now, with that being said, xenon, unfortunately, its formal charge of 0 is when it's just full. Octet's full, doesn't need anyone. Now, with this though, okay, what we can actually do as well as another way to write this down is that instead of just saying it's full, we can actually try to convert each lone pair into 2 bonds. Okay? Now with that being said, you can actually see more closely how then 4 pairs of lone pairs works together to now where you can have 8 bonds if you break the octet rule. Okay, so this is what we're looking at here. They both have formal charges of 0. All the electrons are added to 32. This would be the most stable, I guess, most stable molecule version. And just like that, there you have it. You have the oxygens all double bonded and surrounding the xenon. Okay, so that being said, this is also correct. And now we're ready for question 11, but right after, just check it in to make sure that everything is good on my end. And thank you very much for your patience. Everything seems good to go at the moment. This is more now to the next question. We have, what is a Lewis structure of CH3F? Okay, so with this, alright, we want to be able to first find out, like I usually do, how many electrons we're working with from each atom. Okay, so with that being said, we have a carbon, 3 hydrogens, and 1 fluorine. Okay, so for carbon, being on the 14th column actually would be able to contribute 4 valence electrons. Hydrogen being on the first column is going to be 1 each, so that'll be 3 in total. And fluorine, here's the biggest one, it's going to now be 7 electrons, considering that it's on the 17th column of the periodic table. So we have 4 plus 3 plus 7. We have 14 electrons that we're working with total. Okay, so now let's see what we can do with that 14. I'll put carbon in the middle, considering it has the most unpaired electrons. And we have, this is what we have, CH3F, for at least the Lewis structure, okay? And so we would add every hydrogen, and then we would now add the fluorine. Okay, and now what this has done is that we can now go ahead and add the valence electrons. So we have for fluorine, okay, because, well, the hydrogen is already sharing one of its 1 electron. The carbon is right now sharing 4 of its 4 electrons. So the only ones where the lone pairs can go would be the fluorine indeed, and it would go like this: 1, 2, 3, 4, 5, 6, because the 7th electron is being shared in that bond between fluorine and carbon. Okay, so let's see, do we have 14 electrons? So we have 4 I guess bonds and 3 lone pairs. So in total we do indeed have 14 electrons. And also, is this the best resonance structure? Based on the formal charges, let's see here. Fluorine likes to have a formal charge, well, not likes to have a formal charge, but fluorine's formal charge of 0 is represented typically by 3 lone pairs and 1 bond. Okay, so that one is good for formal charge for fluorine. Carbon, at least for 0, is represented just by 4 bonds. Okay, and with that being said, we are good for carbon. Okay, and the last one, hydrogen, its formal charge of 0, it's just represented by 1 bond. Okay, and that's what each of them does. So with this being said, yes, this is how you draw the Lewis structure of fluoromethane, as they call it. Let's see how our colleague did. 14 electrons surrounding the carbon, okay, and fluorine having the rest of the electrons. And there you have it. This would be the answer for the fluoromethane, and this is correct. And now, for question number 12, we have draw the Lewis structure of BrO4 that has the lowest formal charges. So we want BrO4 minus, okay, giving this more space here. And we want the one that has the lowest formal charges, okay? It's not just that everything just cancels out. That's not what they mean. They mean that it has like throughout the whole molecule, it doesn't have many deviations from 0. Okay, so let's see what we can do here. Bromine. Okay, so let me just write it here. BrO4 Lewis tooth. Oops, sorry, Lewis structure. Okay, so just to reiterate, BrO4 Lewis structure. I'm going to now draw it. So bromine, as I said, that's going to be on the 17th column, so that's 7 electrons. Oxygen, the 16th column, it would be 6 electrons, but there are 4 of them, so that's going to be 24 total, 6 times 4. And now for the last part, we do indeed have 1 extra electron based on the negative right here. So 7 plus 24 plus 1 electron, okay? So pretty much it's 8 plus 24. And so we're working with 32 electrons, okay? So now let's see what we can do with this. Considering that we have only 1 bromine, I'm going to go ahead and put this in the middle for the BrO4. Okay. 32 electrons. And now we're going to just surround it. O, 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 O. Okay? And now, let's see what this bromine can do. We have oxygen, 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 oxygen. And we want to fill out the rest. So oxygen right now is sharing, just make sure, 5, well, one of it's 6 electrons, so I have to label the other 5. 2, 3, 4, 5, 6. Okay? And then 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. Okay? And the last one we have here is also going to be 2, 3, 4, 5, 6. Okay, so there's right now a lot of is that word called again? There's a lot of unpaired electrons. Okay, so now with bromine, all right, this is where we get a little bit of extra help here. Bromine actually now, because it breaks the octet rule, since it was already at 7, it has some limitations of what it can do, but it's still, the goal is that it will surpass or exceed the octet rule. So with that being said, bromine right now is sharing 4 to 7 electrons, so that would be 5, 6, 7. Okay, so the reason why I drew it like that is because then I can just go like this. So it'll be 5, because that one's gonna go into a new bond with the oxygen. Same with this one, and same with, whoops, wrong one, with this one. Okay, so with this being said, what exactly am I saying? I'm saying 3 of those 4 will become a double bond. But we still have an unpaired electron. Well, this actually would be where our, I guess, replacement, if that makes sense. Nonetheless, though, let's just try to at least redraw this, okay? So we have, let me just give myself more space, Br, double bond, double bond, double bond, single. Okay, and now we have this. And like I said, the one extra electron will just be added over to make sure that this unpaired electron now becomes paired. So that one is now complete. Okay, and then we would go ahead and just add that here. So that's what we would have for bromine, I guess, tetraoxide or tetroxide. Now they're asking for the one with the lowest formal charge. This one I usually instinctively solve with the lowest formal charge in mind. But what do they mean by formal charge? Okay, so bromine here actually, if we were to, let me see here, if we were to now draw a formal charge of 0, what bromine typically looks like, it really just be 3 lone pairs of 1 bond. All right, but unfortunately that's not even close to what we have here. Well, the cool thing is though is that for every lone pair you can actually form 2 bonds from it. So with that being said, now we have 7 bonds, which is actually what this bromine has right now. It's 7 bonds total because there's a lot of double bonds. Now, with that being said, the oxygen on the top and the right and left, we have, and this is to stay at home. Well, sorry, not stay at home. This is where it stayed like it is, to where, and by home, that's what I meant. I meant the net of 0, okay, for the formal charge. And now for the oxygen, the bottom though, okay, what's happening here is that it seems to have replaced a bond with a lone pair. When this happens, okay, in this specific case, bond replaced by a lone pair, your formal charge becomes more negative, okay? And there you have it. Now what this makes this extremely cool, actually, at least in my opinion, is that considering that the Br04 minus, the ion itself when it's written out, indicates that there's a negative charge, what we just did here is that we actually revealed where the negative charge is, and that will be on one of the oxygens. And the reason why I say that is because this thing can actually, yes, go through resonance, and any of the oxygens could have been the one that has the -1 charge, and every other oxygen would have had the double bond. Now, with all that being said, yes, this would be the Lewis structure, and I'm glad that our cause is right there, because this is exactly what we got. And they go through why they did that, and you can see here that the formal charge would actually be -1 for that single bonded oxygen, which is perfect because that's what we wanted. This is correct. Now for question number 13. We have, what is a Lewis structure for Ch2 F2? Okay, so Lewis for Ch2 F2. Okay, so now let's see if we can draw this out. Carbon being on the 14th column has 4 valence electrons. Hydrogen, first column, 2 of the 1, so that's 2 in total. And fluorine is actually on column 17. So for these, I guess, atoms here, their valence shell is actually 7. Okay, so that'd be 7 times 2. So that'd be 14 total. So that's 14 plus 4 plus 2. So that's going to be 20 in total, okay? 20 electrons. And we'll see how we can make 20 electrons work. So with this, we put carbon in the middle, okay? And then we put them around it. We have the 2 fluorines and we have the 2 hydrogens, okay? So with this, you might think this is your Lewis structure, but you're not complete yet. You have to also list out, well, not list out, on the picture, add on the, let me check here, just to make sure. What you want to do as well is actually check out and add the leftover valence shell. So let's start with the fluorines, okay? So for fluorine, we're right now just sharing one of its 7 based on the single bond. So it'll be 2, 3, 4, 5, 6, 7. Same thing here. 2, 3, 4, 5, 6, 7. Alright? So we're done with the fluorines. The carbons, on the other hand, is sharing 4 of its 4, so it's complete. And the hydrogen is sharing just 1 of its 1. So it's all perfect. Now let's see if we at least have the formal charges correct for this Lewis structure, just to make sure that we truly did understand this. So that would be, just so I can make sure. For this, exactly the formal charges, we have fluorine, likes to just be like that. 3 lone pairs, 1 bond, which is actually what this fluorine has. Both of them actually. The carbon likes to just be in 4 bonds, which is what the actual carbon has. And the hydrogen is just 1 bond. Now to clarify, exactly, we have these 3 lists. We have to always remember that we first exactly solve for our Lewis, and then these would be our theoretical formal charge of 0. And then based on what you have on your work, you can see, I guess, which formal charge is the best representation for you based on how different it looks from the picture that you have for the formal charge of 0. Okay, so that was kind of a little bit of a jarble, but the point being is that once you draw your theoretical formal charge of 0, you can compare based on how many bonds and lone pair it has for you to evaluate what type of formal charge it actually is. With that being said though, let's see here. This is what we have for Lewis structure. This to me is probably the best one I can think of. Let's see how we did. Perfect, okay? So they do have the fluorines on opposite ends, and I have the hydrogens just next to each other. For these, typically they don't really matter. Why? Because of its geometry, molecular geometry shape. You can see that even with this 2D picture, what's actually happened in the 3D world is that it kind of comes out of the plane in order to be as far from each other as possible. Okay? So that being said though, this is still correct. Okay? And now we have question number 14. Molar mass of fluorine gas. Nice. Molar mass of fluorine gas. Okay? So we have F2. Alright? Now to be able to find this molar mass, we need to make sure that we've accounted for all the constituents. So what that means is that we'd actually go ahead and list it out like this. 2F. Okay? It's, let's see here, 2F times the molar mass, well not the molar mass actually, the atomic mass units of 1 fluorine. That's what we're going to use here, and we're going to multiply it together, okay? So fluorine is actually, based on this periodic table, 18.998. And multiply that by 2, we get 37.996 grams per mole. that would actually be the molar mass of fluorine gas, okay? This would be how we solve that question. Now, with that being said, let's see how we did. We did not forget our units, so that's already off to a great start. And based on our colleague, exactly 38. So they kind of just rounded based on the fact that their numbers were slightly different from ours. But nonetheless, we still got the right answer. So with that being said, this is correct. Move on to the next question. Question 15. We have for question 15. So this is definitely going to be a bit of a doozy here. It says, from the Henderson-Hasselbalch equation, calculate the ratio of dihydrogen phosphate and monohydrogen phosphate components required to produce a buffer solution with each different pHs. Okay, so it pretty much wants you to find the range between these two, I guess, phosphates in order to then find out the, I guess, concentration in terms of the hydronium, aka the acid, or the base, depending. But yes, let's see what we have here. So it's funny actually, because when they talk about phosphate buffer solutions, or at least like the buffers in your body, it most closely resembles this. We actually, I think our pH is around neutral as much as possible in our bodies, and we actually have setups to be able to, you know, make sure that that pH doesn't spike or drop too low. Okay. Now back to the actual question at hand. We have, when they say the Henderson-Hasselbalch equation, that equation refers to this. Okay. pH is equal to pKa plus log A minus over HA. Okay? That is what's happening here. So, with that being said, for this question, we want to be able to produce different buffers, and we just use that based on the ratios. Okay? So, with that being said, a pH of 5.2. The key thing here actually is that we still need the pKa, okay? And the pKa, hopefully you can actually find out the acid and bases sheet, tells us what we'd be, I guess, adding or multiplying with, if need be. So, with that being said, let's see if we can find it, because we have a lot of acids here. Perfect. Phosphoric acid, the second part, which is H2PO4, because that is also known as the dihydrogen phosphate. So perfect. It's 7.21. Okay, so pKa is equal to 7.21. Now let's see if we can actually solve these questions. Okay, so with that being said, our first one, A, pH of 5.2, so that would be 5.2 is equal to 7.21 plus log A minus over HA. Okay, because we're just trying to find the ratio difference. Now, with that being said, we subtract that 7 from both sides. So now we have 7.21 minus 5, 2.21. Well, minus 0.2, 2.01. Okay, so that's negative 2.01 is equal to log A minus over HA. Okay, so let's now convert this over to a power. We have 10 to the power of negative 2.01 is equal to A minus over HA. So that's 10 to the power of negative 2.01. So that's 0.00977. So that's 1, 2, 3. Okay. So that'd be 9.77 times 10 to the negative 3 to 1 for at least the first part. How did I get that? Because once I solved for that 10 to the power of negative 2.01, I found the ratio of the conjugate base over acid. This would be the conjugate base, and this would be the acid, okay, the HA. So I actually put HA there, and this one would just be A minus, okay? So now 7.2 though, okay? We have B, same thing really. So we can take all those steps, but in the end, what we do end up is 7.2 minus 7.21, and we get negative 0.01. And now that's the difference there, okay? And if we did 10 to the power of that answer, negative 0.01, we have a much closer relationship here, okay? So now in this case we have 9.77 times 10 to the negative 1 to 1, which is almost pretty much like 1-to-1 ratio right now, which is really good actually, okay? And exactly the way I calculated this was similar to the top, so that's why I didn't write it down again. Is that you first subtracted the differences, and then you had to undo the log by doing the power, okay? And that's how you got this far. Okay, now with that being said though, let's look at C. pH 9.2. So now the same thing here exactly. We're going to first, what's it called? Subtract the 7.21 minus the 9.2. So that's 9.2 minus the 7.21. We have 1.99, okay? Now, with that being said though, okay, what we have to do here is same thing, or is equal to the log of A minus over HA. And now, what we have to do is find the 10 to the power of 1.99. And by doing that, we actually see this is a much more intense ratio actually. We have a 97.7 to 1 ratio between the A minus and the HA. So hopefully we did this all correct. Let's see what our college got based on this. We have, pH equals pKa plus log A minus over HA. And the pKa, they use a 7.2, but I found a 7.21. But nonetheless, our answers should be relatively close to each other, okay? So, exactly, the ratio of, for the 5.2, the ratio of, that's actually upside down, because it should be, how do I put this? The ratio, there's a lot more HA than A, okay? I would actually say that the ratio of acid to base, in this case, would be 1 to 100. Because you can see here when you do the log, okay, you see that the base divided by acid is 0.001. So to be able to multiply both sides, you'd actually see that there's 0.001 for every 1 or 1 for every 100. So this is actually incorrect. They kind of had it backwards. The ratio luckily is 1 to 1 here, or at least close to it, which is what I got. And the ratio here, when you do that, would actually still be 100 to 1, because this is base to acid, not acid to base. And it only makes sense in a more basic solution for there to be more base than acid, okay? So that's why this is incorrect. The ratios are flipped. It should be 100 to 1 for the more basic solution. The conjugate base is the HPO4, which is why that one had to be the bigger one, at least in the basic one. And then in the acidic one, you just have to flip it over again, okay? So just like how I did. Now for question number 16, I believe, we have what is the Lewis structure of ClF2? Okay, so we have 16 ClF2 Lewis structure. All right. So for this, we notice right away we do have a negative, so this will be an ion. But let's see how it distributes. Okay. So we have 1 chlorine and 2 fluorines. Okay. So with this being said, though, chlorine definitely most likely have to break the octet rule, since it will be the center atom, and it only really has one space for one bond. So with that being said, let's see how many electrons we're dealing with in total. Okay, so both chlorine and fluorine each have 7 valence electrons. So that'd be 3 of them because there's 2 fluorines and 1 chlorine. So that'd be 21 electrons to work with, plus that extra electron. So we have in total 22 electrons. Okay. Now, with that being said, though, we now have to set this up. So we have FClF, right? And for fluorine, each of them are sharing 1 of its 6. So we have here, 1 of its 7. So 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. And now chlorine, on the other hand, actually is sharing, in this case, 2 of its 7. So it'll be 3, 4, 5, 6, 7. And now the only way for this to balance out completely is for that extra electron, which I have not added yet, to actually go and match with the unpaired electron right there. So with that being said, though, this is looking like the most likely Lewis structure. But let's review to make sure that is the case, okay? So do we have 22 electrons? Let's see. We have 3, 6, 9 lone pairs and 2 bonds, okay? And with that being said, if you add it, that's 11 times 2. That is indeed 22 electrons, which is a great start. Now, with that being out the way, let's see what else it says. We want a formal charge of zeros throughout. Can we get that with this? So fluorine, a formal charge of 0 looks like this. That is 3 lone pairs, 1 bond. And that is exactly what this fluorine has. Okay? Now, for the chlorine, on the other hand, it's typically the same thing. Okay, where it's 3 lone pairs and 1 bond. But now, what happens when we, because this is not where it gets extremely tricky, what happens when we turn 1 bond into, I guess, this is actually going to be really hard to rephrase, because we have 3 bonds, okay? So I'm counting that. So that's, 3 lone pairs still, but we added an extra bond, okay? So it's going to be a little bit different, but it's still going to be the same premise. We added a bond and we did not take anything else. To add a bond, that would still send you to have now a formal charge of -1, because now you've gone and added 1 more, I guess, electron. That's what a bond is. It's now sharing the bond with something else. So if we did this, this would connote a formal charge of -1, which is perfect. That's what we want. It is an ion, and it did say that it had ClF2-. Okay, so that is actually what we want there. Let's see what our colleague says for this, because I do believe this is all we need. And so, according to him, we have exactly chlorine, perfect, with 3 lone pairs, all right, and that would be where the negative charge would be, and the fluorines are just following the octet rule as typically and as normal as possible. So with that being said, this is correct. And now, let me just take a quick water break really fast and see how the stream is doing. Okay. Oh, sorry. Let me do that. Open this. There we go. Okay. So we have now a water break. Alright, so now that that's been taken care of, let's hop right back into the stream. We have question number 17 here. Okay, we have calcium chloride, CaCl2, is an ionic compound in which each chlorine atom has lost an electron, or one chlorine atom transferred an electron to the other chlorine atom. Calcium has 2 extra electrons in the innermost shell. Calcium has lost 2 electrons, or calcium has gained 2 electrons. So we have CaCl2. Okay? And now this question is asking which of the statements makes the most sense. Now, with this, alright, we have to actually go back to our periodic table. Calcium, alright, and chlorine are respectively on the 2nd and 17th column. So that means calcium would have 2 valence electrons and chlorine would have 7. Now, in order for calcium to become an octet, would it be easier for calcium to gain 6 more electrons or lose 2 electrons? Hopefully you pick the lose 2 electrons because overall that's dealing with less stress and less effort, okay? So by that, we have the cation of Ca2 plus for calcium, okay? And chlorine, in this case, because it's on the 17th column, has 7 valence electrons. Would it rather give up 7 or just add 1? Okay? In this case, it would rather have 1, which is how we got the Cl minus. Alright? And because we need to balance the charge, we need to then, have 2 chlorines, which is how they got CaCl2. Now, the question is asking which sentence makes the most sense. Okay? As you can see right now, calcium has lost electrons, chlorine has gained electrons. But let's see what each question is saying, well, each answer is saying. Okay, so each chlorine atom has lost electrons. A would be incorrect. Okay, let's just go ahead and do B, C, D, E. All right. One chlorine atom transferred an electron to the other chlorine atom. Not quite either. Calcium has 2 extra electrons in its innermost shell. For this, it's not really about whether or not it's true. It's more so what this has to do with the question. And unfortunately, this has nothing to do with it. What does 2 extra electrons in its inner shell affect how many valence electrons it would have in its outer shell? Which is why this one is not really a right or wrong. It's more so, I guess, excess of information that doesn't really play in. Calcium has lost 2 electrons. So that's the one I think I can agree on, because as we saw with the 2 plus, that means there's a loss, and the 2 means that there's 2 electrons lost. So it's looking like D so far, okay? And E says actually opposite, calcium has gained 2 electrons. In that case, that is definitely incorrect, because as you can see here, we have the 2 plus, not 2 minus. So that being said, the only viable answer here is D. And I do believe my colleague agrees with me as well, to where calcium has just lost 2 electrons. So this is perfect. This is actually what we wanted. So therefore, the 2 plus in calcium means that it gives up 2 electrons. This is exactly what we want to see. So with that being said, now let's now move on to question number 18. So for question 18, we have this. What is a compound name for HClO3? And we have a lot of choices, which is good, because that would make you really think, okay? So now, this is where, unfortunately, a lot of memorization has to happen, okay? What do I mean? HClO3. We have to know almost by instinct what ClO3 is and then from there we can now determine its acid. Okay, so with that being said, name for HClO3. What we really want to know is the name for this ClO3 minus. What is that name? Now, luckily for me personally, I know it, but the question is now, how do I translate to where you can know it? Okay, so with this, ClO3 is a type of a to put this in words, it's like a polyatomic ion. They're very common. They usually like the 8s, so like there's sulfate, nitrate, and all that stuff. The only issue here where I'm pausing trying to explain it is that how do we know it's one of the 8s? How do we know it's not one of the ites? How do we know if this is the correct amount of oxygen attached to it for us to call it an 8? Okay, so that's ATE. The way I like to do it personally, which has so far helped me at least visualize it, is that I like to see if the I guess the oxidation numbers kind of can give me a idea of what the charge would be, and it matches. So what do I mean by that? I mean like just between the chlorine and the oxygens, if I can like find a way to get a charge of -1 based on those oxidation numbers, then I think that's a fair way to say that is a chlorate in this case. So with that being said though, let's see if we can actually enact that. So we have ClO3. When I say oxidation state, I guess not really the oxidation state, because that would actually be quite different. I think what I'm trying to mean is like the valence electrons for at least the chlorine. So in my head, I'm thinking like this. -7. But for the oxygen, that one I'm just using straight the oxidation number, which is known as -2, because there's 3 of them. That would be 6. Okay, and I would actually ignore the charges here. The goal is that we have 7 and 6. Is that a 1 difference to where I can now say that, you know what, it can match that charge? I believe so. So to me, this is a chlorate. Another way that I think is a much more secure way to verify it, but it would require drawing Lewis dot diagrams. That'd be the next best thing I can suggest to be able to see if you can get chlorate to balance out relatively simply. But the only issue with Lewis structure is that it still doesn't tell you like, because what if I said chlorite, for example? I could find a way to draw that and balance it, but it wouldn't tell me whether it's chlorate or chlorite. So this is the best method I can think of. So if I were to rewrite it and I had the ClO3, what I'm saying here is that this 2 from the oxidation number will transfer over here to that 6, and chlorine has 7 valence electrons, so I just like to put the 7 here. And if there is the difference that's enough to account for the charge difference, which is just a negative charge, I think that this would be called chlorate. So that's what I did there. I would just frankly memorize it, because like I said, this is just a way to help me. I personally don't even know how applicable this is to other situations. Nonetheless though, that's what I know so far. So ClO3 is a chlorate ion. Now how do we turn a chlorate ion into now an acid? By adding the H. So what happens actually is that for chlorate ions, you actually have to go ahead and drop the ATE, and it's actually going to be chloric. Okay, you add an IC, but beyond the IC there's a space and you say acid. So this actually, at least in theory, if that one is indeed chlorate, it would be chloric acid. That is my final answer for this. Okay, and let's see what they say. Yep, ClO3 is known as chlorate, and because it's named after chlorate, you have to now end with the IC followed by acid. Okay, so with that being said, HClO3 name is indeed chloric acid. Okay, So let's see now what we can do here, because this is now correct. And we now can move on smoothly to question number 19. We have, how many valence electrons are the atoms? Okay, so there's multiple parts in this. Oh no, wait, these are just the answer choices for this. Okay, so we have how many valence electrons are in the atom selenium, the 34th element, and chlorine, the 17th element. So for question 19, valence for selenium and chlorine, was it? Number say, yep, and chlorine. All right. So selenium being the 16th element, I mean on the 16th column, there's two ways to approach this really. We can just go based on what column they're in, or we can just also go through the electron configuration. The electron configuration can actually show us as well exactly what we're dealing with the valence based on the highest, most outermost shell, which is represented by the highest coefficient number. So let's go ahead and do that actually. So for selenium, just to save us some time here, we're going to actually do the shorthand notation. So I'm actually going to skip all the orbitals and just start with the argon. Okay, so that would be AR. And then we have, because it's going to be on the fourth row, yep, 4s2, 3d10, 4p4. So like I said, you want to focus on the one with the coefficients of 4. I'm actually going to be looking at the superscripts here. So we have an S2 and a P4, okay? Because this 3, this is going to be on the previous, I guess, orbital, shell really. So that's why we don't count it. Now, with that being said though, 2 plus 4, we predict this will have 6 electrons in its valence, which also agrees with the column it's in, column 16. Now for chlorine, let's just go ahead and start at neon. Okay, so this was selenium. For chlorine, we have neon, 3, because now it's going to be on the third row, S2, and it's going to be 3p5. So as we can see, 2 and the 5, we would add it together to where we got 7 valence electrons. And that exactly matches also the column, I guess, because those in column 17 do indeed have 7 valence electrons. So let's see what we can choose here. We have number of valence electrons, selenium is 4. So that one's already incorrect. We cannot choose that because it says chlorine is 5. So it's almost like counting only from the p orbital, which is still incorrect. Number of valence electrons, selenium is 6, and chlorine is 7. That's looking like our answer right there. Then it says 14 and 7, which is not true. Then 34 and 17, which is also not true. So the best answer here would actually be B. So let's see if our colleague agrees. We have selenium belongs to the 6A elements, 6 valence electrons. Chlorine is 7A, 7 valence electrons. Therefore, the answer choice is B. So with that, our colleague agrees with us as well, even with a different method, which is really good. And now for question 20. For the evening, we have lithium nitride, an ionic compound containing the lithium and the nitrogen ion, is prepared by the reaction of lithium metal and nitrogen gas. And now we want to calculate the mass of lithium nitride formed from 56 grams of nitrogen gas and 56 grams of lithium in the unbalanced reaction. So for this, let's try to see if we can write down all the information we have in a nice, concise form. We're given the equation, so that's Li solid plus N2 gas turns into Li3N salt, lithium nitride, okay? And now we're asked to balance this, okay? So, if we want to balance out the nitrogens, because it's an N2 gas, we would need 2 of the lithium nitride. And because now, let me just go ahead and rearrange this so there's more space. Because now there is 2 Li3N, we need 6 lithiums in the reactive sides to account for the 6 lithiums in the product side. This will be the balanced equation, okay? Now, with that being said, though, we have 56 grams of nitrogen gas, so that's right here, 56 grams, and 56 grams of lithium. So with this, we kind of need their atomic masses, or specifically the molar masses of each one. So with that, lithium's molar mass would just be its atomic mass units as well, okay? So if we go over here, lithium actually only weighs 6.94 in this case grams per mole for its molar mass. Nitrogen, on the other hand, is quite bigger because it's N2. Okay, so we have a constituents of 2 nitrogens. So it's not just one nitrogen of the 14.007. We need to double that. Okay, so we actually have 28.014 grams per mole for the nitrogen gas. Now, what about the lithium nitride? In this case, I do believe we will probably need this later. So let's go ahead and find the molar mass for it. So we have 1 nitrogen, so that's 14.007, plus 3 lithiums, okay? And each lithium was that nice 6.94. So that's 6.94 times 3 plus, let me see here, nitrogen would be, how much I do the right math here, 14.007. So that would be 34.827 grams per mole. Like I said, we won't need this now, but we will need this shortly, so I just wanted to get that calculated as well. Okay? So, 56 grams of each. Well, how many moles is that? So 56 divided by the 6.94, because we need to divide it by the molar mass. So grams divided by molar mass is going to be now the moles, okay? And we get 8.06. Well, 8.07 if you want to round it. Moles of the lithium, okay? And now for the nitrogen, we have 56 divided by 28.014. And we get pretty much almost 2. If we round that up, that would be pretty much 2.00 moles, okay? Now, here is the part that's actually funny. You would assume that the nitrogen gases are limiting reagents, but remember, based on the equation we just balanced, it's a 6-to-1 ratio. That is quite a big ratio to be able to fill. Does that 8.07 to 2 equal a 6-to-1 ratio or more to where lithium would actually be the limiting reagent here? Let's see. The 8.07 divided by the 1.99, and as I thought, we have like a 4.04 to 1 ratio. So it's not a 6-to-1 ratio. With that being said, lithium is actually our limiting, and nitrogen gas are excess. Okay? So that means we're going to calculate the mass of lithium nitride formed based on the mass of the lithium we used here, since it is going to run out first, and that's going to be the maximum amount of lithium nitride we can get. So that being said, we're going to convert that 8.07 moles of the lithium to lithium nitride. So that'll be 8.07 moles of lithium times, and the ratio here, as you can see, is for every 2 moles of lithium nitride, there's 6 moles of lithium. And these two can cancel out. And then now, while we're here, we're actually going to just get it straight to its, I guess, mass based on its molar mass, because for every 1 mole of lithium nitride, we have 34.827 grams of lithium nitride. So, with all that being said, we have the 8.07-ish times 2 divided by 6 times 34.827. Okay, so the amount we get formed here actually is a nice and healthy, well, supposedly, if we did this right, 93.67 grams of lithium nitride formed. Li3N formed. So let's see how our colleague did. We have the unbalanced equation as they were trying to solve it as well. Based on the balancing, they got 6 and the 2, which is perfect. That's what we wanted. And then we see the 8.07, nice, and the 2. So far we're good. And because of that, we can now say that the moles of, where is it? Since there's, yeah, based on the balanced equation, we would use the, where does it say it? Exactly, they say lithium, there we go, is a limiting reactant. That's what I was looking for there, so that's perfect, and that's how they use the 8.07, and they were able to get 93.7 grams, which is just a rounded version of 93.67. So with all that being said, this is correct, okay? So that one was done perfectly. This is really good. And before we move on to question 1, we're going to take a quick little break. I will be right back. Let's see. Alright, thank you for your patience, and we're back and ready to kick off last hour of this stream. Start with question number 21. Let me just flip over my screen now. And we have balance the equation and proceed with the calculations. So first we have this. Let's just write it out. NaOH plus H3PO4 turns into Na3PO4 plus H2O. Okay? And the first thing they ask us to do is to balance it out and then proceed with the calculations. Okay? So let's start by balancing this. We have Let me just pick one we want to work with. Okay, that's a good way to start. We have NaOH, so that's one sodium there. But in the product, there's 3 of them. 3 sodiums here. So for this to, I guess, proceed in the balancing out, we need 3 sodiums right there. Okay? So now we have 3 NaOH. And for this case, I'm actually going to rewrite this as just HOH, because that way I know that I'm adding the OHs. And if we have 3 NaOH, we would then need 3 HOH. Reason being because we need, in a sense, to make up for the amount of water there is, because we have 3 OHs now. Okay, we need 3 OHs in the product side. And now the 3H, if we look at the, I guess, reactant side, we actually already have that, H3. So with that being said, this should be the theoretical balanced out version of this. So we have 3 NaOH plus H3PO4 turns into Na3PO4 plus 3H2O. Okay? So now that we have this, let's just double check. We do have 3 Na, 3 OH minus, and there it is, 3 OH minus, its presence in the H2O. We have 3, well, not 3H actually, yeah, actually it is 3H, and here as well, in the H2O there's 3H. So in a sense, we literally do have the 3H2O, so that's perfect. These will line up. And then we have 1 PO4, 3 minus, which is also there. So everything matches up perfectly, so our products and reactants do account for each other. And now it's asking us how many grams of phosphoric acid are required to react with 27.4 grams of sodium hydroxide. So what they're asking for here really is that they want to know how many grams of phosphoric acid is required to completely neutralize or get rid of the NaOH. We don't want more or less, we want the exact amount. So for this, what I'm going to go ahead and do is find the molar mass of each one. The reason being is because we're going to do a lot of conversions here, and I want to be ready and equipped to be able to make all these conversions. So let's start with NaOH, okay? NaOH, that would be, we ignore the coefficients, okay? We focus on just the NaOH. So that'd be 1 Na, 1 O, 1 H. So that'd be 22.99, I think. Let me check actually before I, you have 22.990. That'd be 15.999, and hydrogen is 1.008. We're gonna, these are just the multiplication, and they're all just ones, so this is going to equal each other again. 0, 15.999, 1.008. Add them all together. So for NaOH, we have 22.990. We get 39.997, okay? Grams per mole. So we have 1 down, okay? 39.997 grams per mole. H3PO4, that one, okay, it'll be 3H, okay, because that's H3, and then 1P, and then 4 oxygen, okay? And phosphorus is 30.974, okay? The hydrogen is 1.008, and the oxygen is 15.999. Then we multiply them, that'll be 3.024. Just double check. Yep. And then 30.974. And then we have 15.999 times 4, 63.996. Add them all up. 74 plus 3.024. we get 97.994 grams per mole. So now we have the H3PO4. And then we continue on. We're going to make this a little bit easier for the Na3PO4. We have the P and the O. We just want the 3Na here, okay? So that would be 3 times Na. The Na over there was 22.990. That would be times 3, 68.97. And then we're going to add that with the 30.974 plus the 63.996. And we get 163.94. And now, whoops, so we don't need this. For the last one, the water, okay, that one is just 2H and 1O. That's 1.008 and 15.999. 2 times that, that's 2.016, 15.999. Okay, and we get 18.015 grams per mole. So there we have it. All of them are now calculated and ready for the quick conversions we'll be having to do for this question. So yes, how many grams of phosphoric acid are required to react with 27.4 grams of sodium hydroxide? So let's go ahead and start mapping this out. We start out with 27.4 grams of NaOH, sodium hydroxide. And as we saw, okay, for every 1 mole of NaOH, we need 39.997 grams of it, okay? And then, based on this equation, phosphoric acid, for every 3 moles of NaOH, we needed 1 mole of H3PO4, aka phosphoric acid. And then we have the grams now. For every 1 mole of H3PO4, we had 97.994 grams of H3PO4. Okay? So with this, hopefully our units will all cancel out. Grams of NaOH, grams of NaOH, moles of NaOH, and the moles of H3PO4. Perfect. So what we're going to have to do here in this case, it will be 27.4 divided by the 39.997 divided again by 3 moles because of that ratio, and then multiplied by 97.994. And we get, if we were to round this based on the 27.4, we would need around 22.4 grams of H3PO4, aka phosphoric acid. Now for the next question, it says, how many grams of water are produced from 18.5 grams of phosphoric acid? So once again, we got to do the beautiful ratios. So 18.5 grams, okay, of phosphoric acid. So that would be H3PO4. So now let's start converting. We have 97.994 grams of H3PO4 for every 1 mole of H3PO4. And according to the equation, for every 1 mole of H3O4, there's 3 moles of water. Okay, there's 3 moles of H2O. And now, with this, for every 1 mole of H2O, according to my calculations, there was 18.015 grams of H2O. And now let's cancel our units again. Moles of H3PO4, moles of water, and then bam. So that's 18.5 divided by 97.994 times 3 times 18.015. We get, in total, if we rounded it the same way, 10.2 grams of water. Okay? Now, how many grams of sodium phosphate are produced from 34.7 grams of sodium hydroxide? So, now, same thing again. We start with sodium hydroxide. We have now, let me just make sure, 34.7 grams of NaOH. Same thing again. Wrong one. Based on this, 39.997 grams. So that's 1 mole of NaOH is 39.997 grams of NaOH. Okay, and then we have, oh man, this is just keeps on going. For every, because we want now from the sodium hydroxide to sodium phosphate, so you have 3 to 1, okay? So that's for every 3 moles of NaOH, there's 1 mole of Na3PO4, which is sodium phosphate. And now for every 1 mole of Na3PO4, there's a lot of mass. There's 163.94 grams of Na3PO4. Let me rewrite that. Na3PO4. And now these cancel out. Alright, and we should be left with the grams. And let's plug into our calculator. That's 34.7 divided by 39.997 divided by 3 times 163.94. And we get, so 163.94, we get a nice 47.4 grams. Okay, assuming we've been doing everything correctly so far. Let me just actually add that. For the previous questions, it was grams of water, and this was grams of Na3PO4. And now for the last part, we have how many grams of sodium hydroxide are needed to produce 2.56 grams of water. Okay, so now we're kind of going backwards, but still the same premise. So we have 2.56 grams of H2O. And so as we remember, 18.015 grams of H2O is 1 mole of H2O. And 1 mole of H2O, well actually, we don't even know there's 1. Sodium hydroxide is NaOH, okay? And water. So we put 3 here because each of them is 3. That's NaOH. And then we have for every 1 mole of NaOH, there is a mass of 39.997 grams of NaOH. And let's see now. So 2.56 divided by 18.015 times 3 divided by 3, which is just 1, times 39.997 grams. Okay? And we end up with 5, well, after we cross out the units, 5.68 grams of NaOH. So that is hopefully the breakdown of each question here. Let's see how we did based on our colleague. So we balanced the equation. Hopefully we did it correctly. 3. Oh, they're not. Hopefully not done yet. So there we go. The balance reaction is 3,113, which is perfect. That's what we got. Okay. And now they're doing a lot of conversion here. So therefore, 22.38. Nice. Which is what we got. Well, we rounded up a little bit earlier. Just want to double check to see. Yep, 27.4. So I just kept things here 3 significant digits, because that's what they were using. But yes, so where is it? 22.38, 22.4, same thing. Perfect. That one makes sense. The steps we took were correct. And the same thing exactly. They're still converting again for the water. They got 10.21, which makes sense for our 10.2. So far, we're on a roll. In this case, they got 47.2, but I got 47.4. Interesting. So, oh, I see why. Because they use, I guess the round is a little bit different, but they use 40 grams per mole for the NaOH, and then they used 164 grams per mole for the oh no, wait, it is 47.42. There it is. They just wrote it wrong here, but I'll still count that as correct. But yes, they just wrote it wrong in the answer. It is 47.42. Okay, which is good. And now for the last question here, they got 5.68. The number is slightly different. They could have technically gotten 5.69, but we're still relatively close. And this one is actually due because they actually had different amounts. They had 18 grams for the water and then 40 grams for the NaOH, which does make sense. Other than that, though, this is correct. They did approach this the right way, and they're able to get an answer for each one. So this is a quick recap. Exactly the importance of going through and calculating all your molar masses and then going and doing conversion. It just helps you save time overall. So now for question number 22. For question 22, we have, what is the Lewis structure of NOBr? And it says, do not include overall ion charges or formal charges in your drawing. Okay, which should also not be the case because, well, I mean, we should not have any formal charges of anything that's not 0 because the molecule itself is neutral. So I'm hoping that everything is coincidentally neutral here as well. But we can only find that out by actually drawing it. And it says, do not draw double bonds to oxygen atoms unless they are needed for the central atom to obey the octet rule. So what would even be the central atom here? So for NOBr, nitrogen has 5 valence electrons, considering that it's on the 15th column. Okay, oxygen has 6 valence electrons, bromine 7, because 16th column and 17th column. 5 plus 6 plus 7 is the same thing as 6 times 3. We're working with 18 electrons total. So for this, because nitrogen technically has the most unpaired electrons, I'm going to put that in the middle, okay? Like that. And we have the oxygen and the bromine. So let's go ahead and fill out the, I guess, rest of the valence electrons. So bromine right now is sharing 1 of its 7. So then I'll have 2, 3, 4, 5, 6, 7. Oxygen is right now sharing 1 of its 6. So 2, 3, 4, 5, 6. And nitrogen right now is sharing 2 of its 5. So it will be 3, 4, 5. So right now we have 2 unpaired electrons, and it says do not draw a double bond to oxygen atoms unless they are needed for the central atom to obey the octet rule. Well, the central atom really needs to obey the octet rule here. I cannot give that unpaired electron to the oxygen because then the nitrogen no longer follows the octet rule. So I'm going to go ahead and do that and create another bond. So now what we have is this. Okay, a double bond was made, and now everything should follow the octet rule. I almost blanked out because the oxygen almost looked for a second like it wasn't. But let's see now in regards to its formal charges and in regards to the total electrons. Let's start with the total electrons, okay? So we want 18 electrons, and we have in total 6 lone pairs and 3 bonds. So it's 9 in total times 2. We have 18 electrons. Perfect. Now for the formal charge, oxygen, in order for it to have a formal charge of 0, it needs 2 lone pairs and 2 bonds, which is what it's doing because the double bond counts as 2 bonds. Nitrogen needs 1 lone pair and 3 bonds, which is also what it's doing because once again, that double bond counts as 2 bonds. And bromine, for it to be also at 0, it likes to have 3 lone pairs and 1 bond, which is also what the bromine is doing. So with that being said, exactly, there is no ion charges or formal charges in this drawing because everything has a formal charge of 0, and the oxygen needed to have double bond with nitrogen so that way they could obey the octet rule. With that being said, this is my Lewis structure for NOBr. Let's see how we did. Perfect. That's exactly what I want to see. So with that being said, this is correct. That's what we wanted to see. And let's move on to question number 23. We have ammonia, NH3, is a weak base with a Kb value of 1.8 times 10 to the negative 5. What is the pH of 0.390 ammonia solution? And what is the percent ionization of ammonia at this concentration? This is definitely going to be a big one to solve here, okay? Because technically, what we first have to do is find the pOH. The reason why is I'll actually show you what the ammonia formula does. It's NH3. So actually, let me just quickly write down the information. So NH3KB is equal to 1.8 times 10 to the negative 5. Okay? And we have 0.390 molarity of ammonia solution. We want to know what is the pH. Okay? And then we want to know what is percent ionization. Okay? So, with that being said, we need an ice table, but first we need to know what formula we're working with. We have NH3 plus H2O turns into NH4 plus OH minus. Okay? And now for the K value is usually products over reactants. We just don't count water because water is like the solvent in this case is actually what everything's dissolved in, so we don't use water in this formula. But that means KB in this case, because we are solving the basic side, we do have OH, the products, okay? That would be NH4 plus OH minus over NH3. Okay? So now let's go ahead and draw out the ICE table. Initial, change, and equilibrium. Okay? So the initial for the NH3, as they told us, was the 0.390 molarity. We don't need water, so we can just cross that out. And then the NH4 and the OH minus, we assume we just start with 0 for each. Okay? And now, for the change, is going to be 0.390 minus X. And then for every time it loses the X, right? As in, for every, even we can say 1 mole of NH3 that's gone, if it even got to that point, that means we have actually formed 1 mole of the NH4 and the OH minus. Just like that's what the ratio means. I just said mole, but it could be pretty much for every 1 unit loss of NH3, we gain 1 unit each of NH4 and OH minus. Okay? Now to see what our equilibrium is, for these two it would just be X, right? But for the NH3 it's a little bit tricky because we need to first establish a relationship here. And there are certain rules that follow based on that relationship. If the initial concentration is over 1,000 times larger than the Kb, the change is negligible. You pretty much will end up again with 0.390. You don't have to factor that in. So that's what we're actually going to check right now. So we're going to do the concentration of NH3 over the Kb and see what we get. So 0.390 over 1.8 times 10 to the negative 5. Hopefully it is greater than 1,000, so we don't have to do a quadratic equation for this. So with that being said, we would have, let me see here, 0.390 divided by 1.8 times 10 to the negative 5. Oh wow, that's way above. In fact, we reach over 20,000 times bigger. With that being said, we just save ourselves some work, and we can just say this is pretty much 0.390 for the equilibrium. Why does this save us the effort? Because now when we rewrite our equation, we just have Kb is equal to x squared over 0.390. Allow us to avoid the quadratic equation, and all we're doing is just multiplying now the concentration with the Kb and the square rooting it. So that's 0.390 times the Kb, and then we do the square root of that answer to get that 2.65, it looks like. So then when we do that, we get x is equal to 2.6, well, plus or minus, but because you cannot form a negative amount of concentration, we just say the plus version. So it's 2.65 times 10 to the negative 3, okay? Meaning that the concentration of OH and NH4 we formed would actually be that much, okay? So now to find the pH, this is where it gets tricky, because if we now took the negative log of this, it'd be negative log of OH minus. And that's not the pH, this is the pOH. But let's go ahead and do that nonetheless. So negative log of the concentration of the OH minus, and we get 2.576, well, 577, about there, is equal to the pOH. Now, that is not the pH. To get the pH, we then have to subtract 14 from it, because pH plus pOH should always equal 14, theoretically. Okay? So that'd be 14 minus that answer we just got. And so that means the pH for this question would be 11.423. Okay? That is what we get for the pH, which is great. That's a very good step. Now, for the percent ionization, this one is a little bit tricky, but we'd actually use, I guess, our X value here, because this tells us how much, I guess, of the NH3 dissociated. So what we would do actually is just the concentration of what we have over the equilibrium minus the concentration of like that. Because we don't use a 0.390, we use a 0.390. So that's 2.65 times 10 to the negative 3 over 0.390 minus the 2.65 times 10 to the negative 3. And you'll see what I mean by negligible. Okay, 0.390 minus that, we get 0.387. So overall, there was not really much of a change. Okay, and 0.387 is going to be that divided by that, and then once we do that, we times it by 100 to get a percentage. So the amount it ionized in this case would be a 0.684% ionization, because that's pretty much the amount that it dissociated. So I didn't have to exactly pick out a bunch of them. I just had to use that X value, because in a sense, like we had that ratio is kind of just 1 to 1. So every 1 unit, think of it this way, that in terms of the 0.390 that we had, 0.265 times 10 to the negative 3 units of it ionized, which is why we can do that formula. Actually, I don't think we subtract. That is, because now that I think about it, it wouldn't be a subtraction. We would actually just use the 0.390, because of the fact that we're saying of the total, how much of it ionized. So that was my mistake there. And so, although the number doesn't change much, it's important to be as accurate as possible. Okay, and we get 0.679 instead. So yeah, it didn't change much, but it's just important to be able to follow that, because now that I phrased it and actually worded it out, that 0.390 would need to be there, because that's of the original amount, how much of it ionized. So it'll be a percentage like this. Okay, so with that being said, let's see how they did. They did the ice. They did the quadratic equation, I'm guessing, because they have the 0.39x there. And they got 2.64 times 10 to the negative 3. Not really much of a difference there. They got the pOH, which is 2.58. And funny enough, they still end up with a pH of 11.42. So that's perfect. We got that part correct. And then the percent ionization is just the 0.264 over the 0.39, and they get 0.68. So awesome. Both is correct. So now let's move on to question number 24. They want us now to name each acid. That's what reminds me of, okay, yeah, that's pretty funny. It's like, oh, you're a chemist, name every acid. But nonetheless, let's try to name every of the acids listed here. So we have A, HI, B, HNO3, and C, H2CO3. So for this, they were relatively kind to us, okay? I would actually go ahead and go with B and C first, because they were kind to us because they were actually able to give us the 8s. What do I mean by 8s? These right here, which is I guess they're the anions, the polyatomic anions, that is known as nitrate ion, and this is known as carbonate ion, okay? And they have very specific naming rules when it comes to changing that into an acid. What happens is that you drop the 8 in ion and you add ic acid, okay? So this would actually be nitric acid, and carbonate would be carbonic acid. Okay, because of the fact that exactly these things kind of have to be memorized. I am quite familiar with the different types of polyatomic anions, so I can recognize them quickly. But that is what you need to be able to do for yourself, is that it's not just a mere ignoring of the hydrogens, but it's more so specifically recognizing what the polyatomic ion is supposed to look like. The reason why it gets tricky is because there are different versions, and each of them have different varied amounts of oxygen, which is why you kind of have to really first focus on memorizing your different types of 8s and how many oxygens each of them has. I know right away carbonate is 3 oxygens, same with nitrate, which is why I could pick up that they were nitrate and carbonate. So that would be those two, nitric acid and carbonic acid, right? Now this one is a little bit different. We don't try to call it iodate or anything because there's no oxygens there. For this one, it has specific naming where you just say hydroiodic acid, because when you have an well, let me just move this over there like the rest of them. When you have an iodine, okay, what happens here, well, iodine ion, same thing where you drop that, but because it's not an 8 or an ite or any of those, you actually have to now designate a hydro in front of it. Okay, hence how we got hydroiodic acid. Those would be the names for each acid. Hopefully my colleague agrees. So let's see here. A hydroiodic acid for A, perfect. Nitric acid for B, perfect. And carbonic acid for C. Fantastic. So with that being said, this is correct. So now we're going on to question number 25. We have, what is a Lewis dot structure for chloroform? CHCl3. Okay? And what is electron pair and molecular geometries, and what orbitals are on the C, H, and Cl overlap to form bonds involving these elements? This is definitely a tricky question, but let's try to break it down. So the first thing first, the Lewis dot structure for chloroform. CHCl3. Okay? So carbon being on the 14th column, that's 4 electrons. Hydrogen, that's 1 electron. And chlorine being on the 17th column, that's 7 valence electrons, but there's 3 of them, so that's 21. So we have 4 plus 1 plus 21. That's 26 electrons total. And now let's go ahead and try to sketch this out. We have carbon in the center. Then we have, just like that, Cl, 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 and H. So now for all the chlorines, okay, we want to actually now add the rest of its valence electrons, because right now it's sharing 1 of its 7. So it'll be 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. Okay. 2, 3, 4, 5, 6, 7. Now, with that being said, though, we now have to make sure that this is actually 26 electrons. So we have, if I can read this correctly, 3, 6, 9 lone pairs and 4 bonds. That's 13 in total. Double it, we do have 26 electrons, so perfect. Okay, and now with this being said, we have to make sure that all the formal charges are hopefully 0. So chlorine, for it to have a 0 formal charge, is 3 lone pairs and 1 bond, which is what every chlorine does. Perfect. Carbon is just 4 bonds, which is what it's doing. And hydrogen, for a formal charge of 0, just 1 bond. So this indeed would be the best Lewis structure for CHCl3. Now it's asking what is electron pair molecular geometries. So to find the electron pair geometry, we actually have to find, I guess, the zones, I guess the things that the carbon is bonded to. And right now what I count is just 4 bonds, okay? So that would be 4 bonds and no lone pairs. But this shape, okay, for it to have 4 in total is known as tetrahedral for its electron geometry. Alright? Funny enough, actually, because there's only 4 bonds, to be more specific, the shape is still known as tetrahedral for its molecular geometry even. Okay? And now, for it to have a tetrahedral, it actually tells us the hybridization. Based on the shape, the carbon, okay, carbon is sp3 hybridized. Okay? And that's very crucial because it tells us now what orbital carbon will be using to overlap with the hydrogen and the chlorines to form bonds involving these elements. So hydrogen actually, funny enough, only has, if we actually wrote it, it would be 1s1. But pretty much it only has an s orbital. That's all hydrogen has. So because it has an s orbital, C2H is sp3 to s orbital overlap. That would be all there is to it. And now for the C2Cl, assuming that things like to go from the lowest energy to the highest energy, because chlorine technically would be like I think it's on the 3rd row, but let me, yep, 3rd row. It would be kind of like for its most outer shell, it'd be 3s2, 3p6. Because the s2 are the base right here, and then the p's go higher and higher, we would actually be using the p orbital in the chlorines to overlap. So carbon chlorine would be sp3, because this whole thing is hybridized. Okay, that's why we have the sp3, and it'd be 2, the p orbital overlap for C to Cl. So this is a review. We have exactly C to H, sp3 to S, C to Cl, sp3 to P, and they're both tetrahedral for its electron geometry and molecular geometry, and we also have the Lewis dot structure. So this would be more of like its 3D shape, nonetheless can still pass the Lewis dot structure. And in terms of the molecular geometry and electron pair geometry, it is indeed tetrahedral. And since carbon has 4 valence electrons, its s orbital is filled and 2 p orbitals are singly occupied. So it's now, when Cr is bonded with 4 other elements, is now using s orbital and 3 p orbitals. Okay, and that's actually how we got sp3 hybridized. So with that being said, hydrogen only has 1 electron in the s orbital. Thus, the orbital used to form a bond for a hydrogen atom is in the s orbital. So that's why it's sp3 to s orbital overlap. The chlorine only needs 1 more electron in order to follow the octet rule. And that one would be its most outer, the top one, the 3p, or at least the p orbital. So we'll probably use the 3p, and it says Z, but the important thing here to recognize is it wants to use a p orbital, and it will use that to pair it with the sp3 hybridized on the carbon. So that would be the orbitals that overlap there. Okay? With that being said, this is correct. And exactly, like going beyond even the Vesper theory, it's good to just know exactly like what orbitals in the order it goes. I know that there's like a 3py, 3px, and then there's a 3pz as well. And I do believe 3pz is the highest one. But the point being, though, is that you have to recognize that the carbon and the chlorine would interact based on the p orbital of the chlorine, because that's the most outer shell. and that's just the, I guess, easiest access. Okay. And now for question number 26. We want to know what the Lewis structures of CHFCl2 are, and then CHF3 and CClI3. Okay. So Lewis structure of 3 molecules. Okay. So we have CHFCl2, CHF3, and CClI3. Luckily for us, they should be relatively the same shape, almost, where it's like tetrahedral. But before we get that far ahead, let's just see how many electrons we're working with in each. So carbon, that is 4 electrons because it's on the 14th column. Hydrogen on the first column is just 1. Fluorine is 7, and the chlorine is times 2, that's 14. So that's 4 plus 1 plus 7 plus 14. That is going to be 18 plus 8. I believe that's 26. Let me just check, because there's no point in being wrong here. Plus 7, we have a calculator. Plus 1 plus 4. 26 is indeed the answer. And for this thing, similar, but it's now 3 of these. So we have instead CHF3, that'd be 21. And funny enough, this still adds 26 electrons. And then for the last one, because we have the most halogens on it, okay, that would be 7, and this will be 21. So that's 28 plus 4, that's 32 electrons. So we can actually just go and draw almost all of them at the same time, because it really would just be like copies of each other. Okay. So we have this. And now we can actually go and be specific. So we have H, F, Cl, Cl, H, F, 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 and then Cl, I, I. And now you can just go ahead and fill out each of the valence electrons on the outer shell that need it. So hydrogen, exactly, it's already sharing one of its 1, so it's good. But fluorines are all sharing, well, let me just, before I even start filling them in, are sharing one of its 7. So it's 2, 3, 4, 5, 6, 7, 2, 3, 4, 5, 6, 7, 2, 3, 4, 5, 6, 7, 2, 3, 4, 5, 6, 7. Okay, and the chlorines all here are sharing same thing, one of its 7. So 2, 3, 4, 5, 6, 7, 2, 3, 4, 5, 6, 7, and 2, 3, 4, 5, 6, 7. And then the iodines are all sharing same thing, one of its 7. So 2, 3, 4, 5, 6, 7, 2, 3, 4, 5, 6, 7, 2, 3, 4, 5, 6, 7. Awesome. So, with all that being said and done, we now have the 3 Lewis structures, hopefully. Let's first compare the electrons to make sure we have it correct. So, the first one has 3, 6, 9 lone pairs and 4 bonds. So that's 9 plus 4, that's 13. Double that, we do have 26. So perfect. Same thing for the one actually next to it, the one in the middle. It has 9 lone pairs and 4 bonds. And the last one has 12 lone pairs and 4 bonds. So that's 16. Double that, we do indeed get 32. So that's good so far. Now to make sure that these all have the formal charge of 0, hydrogen, when it has formal charge of 0, just 1 bond, which is what the 2 hydrogens are doing. Carbon, when it has a formal charge of 0, is just 4 bonds, which is what every carbon is doing. Chlorine, when it has a formal charge of 0, is 3 lone pairs and 1 bond. Same thing with the fluorine, 3 lone pairs and 1 bond. And even the iodine is 3 lone pairs and 1 bond, which is what everyone's doing. So all of these actually follow as well the formal charges of just having 0 throughout. So with that being said, I have now drawn the Lewis structures of all 3 molecules. So the first one, yep, that's what I got. Second one, just a bunch of fluorines, perfect. And the last one, CClI3. These are all correct. And now for question number 27. Okay. We have hydrophobic substances such as vegetable oil. So hydrophobic substances like oil are blank. Let's try to discuss what these are. We have A, B, C, and D. I won't write them up, but I will cross out the ones that don't make sense. Okay? So, now, what does hydrophobic mean? Well, typically hydrophobic means water fearing, or I guess water avoiding. So that is a key part that we need here, okay? Oil, or vegetable oil, is water avoiding. It does not mix with water. And you can actually see that when you try mixing oil with water, or when you're trying to, for those that can't relate, when you're trying to wash oily dishes without soap, it's very painful because the water and the oil just kind of slide off each other and you're still left with an oily plate. But nonetheless, that is what I want you to think about when you think about hydrophobic. So let's go through the answers, okay? We have a nonpolar substance that repels water. For this, I'll actually just put a dot here because that sounds like a pretty good explanation. The key part is that it repels water. That and water do not mix, okay? Now, it says a nonpolar substance that have an attraction for water. The key part isn't the nonpolar, it's just the fact that it says the attraction for water part. We don't want that. So B is not it. Polar substance that repels water. So we're actually going to start this as well, because we're going to discuss A and C to see which is our best choice. And the last one is polar substance that have an affinity for water. Once again, we do not want that affinity. Now, for this is where it gets tricky. Alright? I personally know the answer through experience, but the way you figure this out is let's actually talk about water itself. Water, if you quickly draw its Lewis structure, is a polar molecule in itself. And polar things attract polar things. That's just it, because if you're polar, you have a positive and a negative side. Here the oxygen is where the negative is, and the hydrogen are where the positive sides are. By just having a positive and a negative sides, you almost literally cannot be a polar substance that would repel another polar thing. Because if you repel the negative side, you attract the positive side. It just flip over and bam, you're attracting it. So polar substances just can't repel other polar substances. They'll find a way to attract each other, whether it's through reorientation or something like that. But non-polar substances, that one is where now there's no way, in a sense, for the water to really, I guess, get attracted to it. There's no polarity to it. There's no part that, I guess, serves as a way for water to even attach itself. So that's why C would not be a good answer, because once you start talking about polar substances, it's really hard for you to say that, yes, this does repel water. So in this case, as my colleague said, based on right there at the top, the answer choice is A. It is a non-polar substance that repels water. How do we know actually that oil, vegetable oil, is a non-polar substance? Because when you think actually of what it's composed of, the fatty acids and the, I guess, fatty acid chain and glycerol, I think, all those things are, no, not glycerol, that's something else. But the fatty acid chain, all that part is just kind of like hydrocarbons got bonded again and again and again, and it doesn't really have a polar aspect to it when you're dealing with hydrogen and carbon bonds. Okay, so exactly, hydrophobic substances refer to substances that hate or do not mix well with water, and they're of opposite polarity to water, or technically non-polar. And since water is polar, hydrophobic substances are non-polar. So this is correct. So let's move on to question number 28 now. What is the Lewis structure for xenon dioxide difluoride? Something like that. Pretty sure the name is wrong. Ch2 F2. And then we want two resonance structures for it. So after we draw it, I think it's asking maybe for two more, which I do not mind doing at all. So with that being said, first things first, let's finish writing the question. Resonance structure. Okay. So we have Xeon F2. So xenon actually will have to break the octet rule for sure, because it is a noble atom, and those ones already have 8 valence electrons. It really doesn't have any purpose actually forming bonds with other things. Yet here we are. Oxygen, okay, is on the 16th column, so that'd be 6 electrons that we're working with, and there's 2 of them, so that's 16. Okay, fluorine, same idea, there's 2 of them, but it's actually from the 17th column. So in this case, we have, I don't know how I got that, 16. I'm thinking of the mass. Oxygen, that's 6 electrons times 2, that's 12. Fluorine, that's 7 electrons times 2, that's 14. There we go, much more sense. So 12 plus 14 plus 8. We have 34 electrons we must distribute, okay? So let's see how we can do that. So we first have xenon in the middle. We just attach these O, F, F. And then let's see what else. We can then now go ahead and start filling out the valence electrons for each one. Oxygen is sharing one of its 6, so that'll be 2, 3, 4, 5, 6. And then same thing, 2, 3, 4, 5, 6. And then the fluorine is one of its 7, so 2, 3, 4, 5, 6, 7. Same thing here, 2, 3, 4, 5, 6, 7. And there you have it. Well, not quite, but xenon, because xenon needs to be filled as well. And right now, xenon is sharing 4 of its 8. So it might do 5, 6, 7, and 8. And you're probably wondering why I went ahead to make 2 of them unpaired rather than pairing them, because this would be the best way for xenon to then form a double bond with the oxygens, allowing the oxygens to then stop being a, allowing the oxygens to stop having just that one unpaired electron. So, with that being said, we have now, there we go, forming a bond. And then this as well, to form another bond. So now if we rewrote this for our first of the 3 resonance structures, we have xenon double bonded to these oxygens. We have a fluorines. Okay. Okay. And then we have, So, with this being said, let's just check first if we have 34 electrons, okay? So we have 2, 4, and then plus 6. So in total, we have 10 lone pairs, and then we also have 2, 4, 6, 7. Oh, it's 2, 4, 5, 6. That's 10, and then just trying to make sure I do the math right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh yeah, that's why I was missing one of the xenon. There we go. We have 11 lone pairs. Cannot forget this guy here. That's why. Can't forget that one. So that's why we have 11 lone pairs, and then we also have 1, 2, 3, 4, 5, 6. So 11 plus 6, 17 in total. Double that, we do indeed have 34 electrons. And now, in order to, I guess, do this part, let's just check to see, other than the xenon, if we have a, I guess with the xenon, the formal charges all make sense. So oxygens, for this formal charge to be 0, we need this. 2 bonds and 2 lone pairs, which each oxygen does. So perfect. Fluorine is going to be 3 lone pairs and 1 bond, which each fluorine does. And now for the xenon, it's supposed to be just 4 lone pairs. Well, if we turn some of these into bonds, hopefully we can match the picture. So for every lone pair, we need to make 2 bonds. So in this case, if it still has 1 lone pair, it needs 6 bonds, which 1, 2, 3, 4, 5, 6. So xenon actually still has a formal charge of 0. So now, when we actually want to draw the Lewis structure in this case, we can do quite a few things, depending. We can make it so that the xenon is the one that has the plus, because I would actually rather keep the fluorines neutral rather than messing with them, and have the oxygens turn negative and the xenon turn positive. So what do I mean by that? If I went ahead and did this, because I already broke the octet rule, there's not really much sense to try to quote unquote keep the same form. But if I went ahead and did that, I would then have this form as a possible resonance. Okay. And then you would see, although the fluorine stayed the same, it's just this one oxygen that now, because it replaced a bond with a lone pair, it actually now would have a charge of -1. Okay. And xenon, actually, if you check now, sorry, I almost forgot it's a nice lone pair. If you check now, it actually now has 1 lone pair like the picture, but it has 1, 2, 3, 4, 5 bonds. It lost a bond, which is why I got positive. That is one possible resonance structure. But what if I really wanted to mess xenon up and say, you know what, everyone else gets a negative? I could also do this. If I moved this bond here outside as well, xenon now, although this may be unfavorable, we don't really know because xenon already broke the octet rule. So we're kind of just doing what we can. We have now everything is a single bond. One, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And I'm surprised it still has this nice little lone pair here. But the point being, though, is that now we have negative here, and 2 plus here. Instead of it being 1 plus, it's now 2 plus. Because it's lost another bond. Okay? And that would be another possible resonance structure right here. And any of these could happen. It could have even, like, another resonance structure could be that Xenon instead gave it to the oxygen on the top first, for example. But these are just some ideas of resonance structures for it. Just because in this case you should see that we still have 34 electrons in total, which I will check actually for the last one, because we have here 3, 6, 9, 12, 13 lone pairs, and then we have 1, 2, 3, 4. So 13 plus 4, that's 17. So that is indeed 34. So let's see how they did it. So they have, interesting, can't really tell what they mean by that red dot. What they did exactly, they moved the xenon, one of the bonds from the xenon out to be able to get the resonance structure like I did here, for example. Okay, but instead of continuing to move another one out and really mess the xenon up, what they decided to do instead was to reverse the change that they did and push the other one out. Like I said, this one I could have also done it to where I did xenon, and then now the double bond is here and the single bond's up top. I could have easily done that as well as another resonance structure. There's quite a few possible resonance structures for this, and these are just some of the few. I can say that most likely, because this will be the negative and this will be the positive, that this one will be quite unstable here, this one here, because for now it to be 2+ for formal charge, it's just getting further and further away from where it wants to be, and that is just a huge no-no. It does not want that. So yeah, that would be the answer to this question. This is correct. And just exactly when you're doing the resonance structures, I'm glad this one didn't ask in terms of like which one would be the most favored. It would definitely be this, and then it'll probably rank in order like these two would be the next most favored, not this one here, because these ones are working with just one change each, like I guess one step over or minus, but this one has 2 steps of a change. So now for question number 29. We have, what is a Lewis structure for HO2? Did not know even that existed. Hydrogen superoxide. So HO2 Lewis. Okay. So now for this, we're just gonna break it down as we've been doing. We have one hydrogen, which is just one. That's gonna be interesting actually. Which is just one. I guess what's that? Wow, I blacked out the name. Valence electron. And then we have 2 oxygens, which 6 valence electrons each, so that's 12. So that's 13, interestingly, electrons we have to work with. So with this, I'm going to assume here that one of the oxygens is in the middle, because hydrogen can only have one bond. And it's going to be something like that. That's what we're going to start with, okay? And I'm going to go ahead and fill out the electrons for each of the oxygens. So we have 1, 2, 3, 4, 5 of the 6, because the oxygen is using the 6th one. And then this one has a bond of 2. Oh, this is going to be very strange. I mean, this one has 2 of its 6 being used, so that would be 3, 4, 5, 6. Huh. I can't tell you what to do here. There's O2, and that's definitely 13. Interesting. Interesting. I don't know. This one got me. Because no matter how we draw it, I'm still left with something uneven. If I put the hydrogen in the middle, that just breaks, like, hydrogen can't really do that. So I'm curious to see what my colleague has to say about this question. Because exactly, the total is 13 electrons. So it really is just that. Wow. Okay. Very interesting. It just has, I guess, a radical or just an unpaired electron right there. Good to know. Well then. Very interesting, because this oxygen here, we couldn't really say that it has a, I guess, formal charge of like a whole number even. This is like missing an electron. But it's, yeah, this is a very strange one indeed. Let's see if we can, I guess, kind of pseudo guess our way through it. If we use the equation for the formal charge, it would be 6 because the oxygen has 6 valence electrons, and then it has, how many electrons does it have to itself? 5 electrons, weirdly enough. Okay, that'd be plus, how many electrons is sharing? 2 over 2. So that'd be 5 plus 1. Oh, that's strange. That's very strange. It's also 0. This is also a formal charge of 0. Who knew? Okay. Well then. That's got me thinking. So, exactly. We still have a value of 13. There is just one unpaired electron there, and that is its form for hydrogen superoxide. At least that's what they said. Yes. So with this, I think the lesson here really is that if you can't make it work, don't force it. There are some things in nature, as for example this one, that do come in just a radical form. So this is correct. There's nothing else we can do to change it. No matter where we try to move this unpaired electron, it wouldn't be a way to where it disappeared. It would always be present. So yeah, very strange, very interesting actually. So now for question number 30, our last question for tonight, we have the Lewis structure of methanethiol. Lewis of CH3SH. So luckily for me, I am quite familiar with the specifically like what a thiol is. So a thiol is just an SH group. Okay, so if you think about it in regards to, like, for example, methanol, where we have methane with CH4, where we have this. Okay, what we're doing here is that instead of it now replacing an H with an OH for the alcohol, the methanol, we're replacing an H with an SH. Okay, that is what we're doing here for this question. Nonetheless, let's just try to solve it itself. So we have carbon, that's 4 because it's on the 14th column. Hydrogen in the first column, there's 3 of them, so that's 3. Sulfur, 16th column, that's 6. And then the last hydrogen, that's 1 again. So that's 4 plus 3 plus 6 plus 1. So that's 4 plus 4 plus 6. That's 8 plus 6. We have 14 electrons total. And now, let's go ahead and set it up. We're going to put, based on how we kind of mentioned the thiol, we're actually going to put the carbon and the sulfur next to each other, okay? And then we just have 2, 3, and 1. And so we're trying to now structure out the Lewis for this methanethiol. Okay? So now we're going to fill out the electrons left over into like the valence shells. The only one we can really do is sulfur, because right now it's sharing 2 of its 6. So it'll be 3, 4, 5, 6. Carbon's already satisfied and the hydrogen's already satisfied. So now, just to check to see if we have 14 electrons, we have 2 lone pairs and 1, 2, 3, 4, 5 bonds, 7 in total. That is 14 electrons. And now for the last part, we're just going to quickly check the formal charge. We have formal charge of carbon of 0 is just 4 bonds, which is what it's doing. Sulfur is just 2 bonds and 2 lone pairs, which is also what it's doing. And the last one, hydrogen, is just one bond, which is what it's doing. So all of these are representations of a formal charge of 0, which all of them are coinciding with. So this will be a Lewis structure of methane thiol. As you can see, the thiol group right here is what replaced the hydrogen and just took a spot, which is exactly what we have here. So that's perfect. This is what we should get, and that is correct. So let's submit that. I believe, like I said, that's the last question for today. Awesome. So with that being said, I'm just going to quickly wrap up. We did go over quite a few topics here, but thank you nonetheless for your patience. If you have any other questions or you just want to delve deeper into any of the topics we covered today, definitely check out the links in the description below. With that, you have a great rest of your evening, great rest of your weekend, and see you next stream. All right, goodbye now.